Alright, this is the video for the study guide that I'm giving you in class on Wednesday to prepare for the Unit 4 test on Thursday. So the first thing we did in class was learn how to read and write chemical equations. By reading a chemical equation, that means interpreting it or taking the chemical equation and writing a sentence from it. Now, I'm not going to go through and read all these points to you. But again, these are some of the key things you have to remember. When it's a compound, you have to decide if it's ionic or covalent so that you use the correct rules for the nomenclature. If it's an element, you have to watch for diatomic elements. Writing down symbols, like what do you do with the plus signs, what do you do with the arrows. Remember, the tricky part in that is dealing with the arrow when you have just one reactant or no plus sign on the reactant side. Making sure you use the decomposes to produce instead of just saying to produce. That way we get a verb in our interpretation in our sentence, and then knowing what those abbreviations for the states are. Now, what I did in my answer key is I underlined all the names of all the substances, and I just want to make sure you understand where those names come from. And I just start on the left and I work my way to the right. So ALS is solid aluminum. That has one capital letter in it, and that's what makes it an element. And whenever we're dealing with an element, we just write down its name straight off the periodic table. We don't do anything to it. Plus sign on the reactant side gets replaced with reacts with. And we get to our next thing. It is aqueous. So I use that term there. And then H2SO4. Now, it does start with a nonmetal, but hydrogen is one of the weird exceptions to almost all the rules. We treat hydrogen just like it's a metal. We name this just like we would any ionic compound. You write down the name of the positive ion, which is hydrogen, and then you take care of that negative ion. This is a polyatomic ion. The SO4 is on our table of polyatomic ions. It is sulfate. So again, we just treat the hydrogens like it's a type 1 metal. The arrow here is going to be to produce. We do have that plus sign there, so we just use the to produce. Now H2, this is one where students will make mistakes. H2 is just one capital letter, so it is just an element. That element is hydrogen. We're not going to do anything with that 2 because the only time we do anything with those 2's and the prefixes like di is when we have a covalent compound. Again, this has just one capital letter in it, so it is not a compound. And then finally, aqueous this. That's ionic because it starts with a metal. Al is aluminum, and again, SO4 is on our table of polyatomic ions. It is sulfate. Remember never to change the ending of a polyatomic ion. Just write down the name as it appears on that table. Remember, sometimes we have to use Roman numerals with these ionic ones. In this case, we did not, because we can look up the oxidation number for the aluminum. Roman numerals are when we have a metal for which we can't find the oxidation number for, like iron. So again, this has one capital letter in it. That makes it an element. That is carbon. It is a solid. This is an ionic compound. Iron is a metal. That's how we know it's an ionic compound. So it's iron for our metal. The oxygen becomes oxide, using that IDE ending because it is a non-metal for my negative ion. Iron is going to require a Roman numeral, and the reason for that is because we can't look up its oxidation number on the periodic table. So what we do is we start over here on the negative side. There are 3 oxygens. Each oxygen has a -2 charge. So 3 times -2 gives us a charge of -6. That's the negative side of our compound. We know the positive side has to cancel that out, so the positive side has to be +6. We're going to divide that up by the number of metal atoms we have. We have 2 of them. So each one has a +3 charge. So we put that 3 in the middle of the name as a Roman numeral to tell anybody who looks at it, that the iron had a +3 charge. CO is covalent, 2 nonmetals. We're going to use the prefixes there. Remember, you can't use mono on the first element, so it's just carbon. And then when we put mono on the oxygen, we are going to drop the O, so it's going to be monoxide, not monoxide. And then finally here we have just an element, one capital letter in it. Fe is just iron. And again, throwing those states in there as we go. Carbon was a solid. The iron 3 oxide was a solid. The carbon monoxide was a gas. The iron is a solid at the end. Again, plus signs on the reactant side or reacts with. When you have that plus sign there, that arrow is to produce. Plus signs on the product side are always and. Got it, iron again, so we have another Roman numeral to figure out. And again, we always start over here on the negative side of our compound. There are 2 chlorines, that is based on that subscript 2. The oxidation number for chlorine, because it's in group 17, is -1. So my total negative charge is -2. My total positive charge has to cancel that out, so I know the positive side has to be +2. There's no subscript on the iron, so that means 1. So that iron has to carry the whole +2 charge, thus the Roman numeral 2. It is an AQ, so it is aqueous iron 2 chloride. Again, remember, change the chlorine to IDE. Plus sign on my reactant side is reacts with. This is aqueous Na2S. So aqueous. Na is sodium. Sulfur becomes sulfide. That is an ionic compound because of the metal. Because our negative ion is just a nonmetal, we use the IDE ending. Arrow is to produce. Our next substance is a solid. Remember, the oxidation numbers are not going to change. If you see these transition metals in a compound from one side to the next, you figured out it was a +2 over here. In this compound over here, it's also going to be a +2. So it's iron 2 sulfide. We did lose the Roman numeral in this one, and that's only because we went from a compound to an element. But if it's in the compound on the reactant side, and if it's in a compound on the product side, like we have here, those Roman numerals are going to stay the same for you. In fact, this is a double replacement reaction, and all the ions stay the same. We had iron 2, we still have iron 2. We had sulfide, we still have sulfide. We just swapped it around and changed the ions up a little bit. We started off with sodium, we still have sodium. We started off with chloride, we still have chloride. We just rearranged those names in those double replacement reactions. And that is the way it always goes. All right, let's move on to page 2, where we go the other direction, writing the equation from the sentence. Again, we got to make sure our sentences are in order. Make sure reacts with is the first thing you see in that sentence. If it's not, you know that whole sentence is written backwards, and you're going to kind of have to work from the end back to the beginning again. All of these, the first thing you're going to see is reacts with. So in all of these, they are in the correct order. So we just work our way through the sentence. Again, I'm not going to read everything at the top word for word, bullet point for bullet point. Just remember, if you're dealing with an element, its name is exactly the same as it is on the periodic table. Just remember, this time you have to look for the diatomic elements. You have to put those subscripts 2 on them if you see them. For the compounds, you got to figure out their ionic equivalence. So if you know if they're crisscross or not, you always crisscross with ionic compounds. You just use your prefixes and your covalent ones and do your correct formatting. Reactants first, then products. Put the arrow in between if you have more than one reactant, plus signs in there. More than one product, then plus signs in there. So we're starting off with hydrogen chloride. Hydrogen is a +1. Chlorine is a -1. Again, hydrogen we're going to treat like it's ionic. We're going to treat it like it's a type 1 metal. And since we have a pair of 1s, we just end up with HCl. It does say aqueous in the sentence, so we do put that abbreviation on there. Now we move on to calcium carbonate. Calcium is a +2. It's in group 2. ATE ending on the carbonate means it's a polyatomic ion. So you look at your table of polyatomic ions. Carbonate is CO3. Carbonate has a -2 charge. So we're going to have a pair of 2's here, which must be reduced to 1's. So it is just CaCO3. And it says powder here. Powder is one of the words we can use to describe a solid. That's why it says solid in the equation. Now you're on to calcium chloride. Calcium is a +2. Chlorine is a -1. The 2 goes there. The 1 goes there. That's how we ended up with CaCl2. And it does say an aqueous solution, so we put AQ on it. Water is always H2O. It tells us it's a liquid. And then carbon dioxide, we see that di there. That's covalent, so we just write down what the name tells us to write down. There's no prefix on the carbon, which means it's supposed to be 1. It was supposed to be mono there. Rule is we can't use mono on the first element. So carbon is just C. Dioxide means 2 oxygens. And again, it does tell us it's a gas, so you want to include that in our equation as well. Aqueous, AQ, iron 3 chloride. Again, the 3 means the iron is a +3 ion. Chloride IDE is just chlorine. Most of the time you see the IDE, it's just a nonmetal. It's in group 17, so it's a -1. 3 goes there, 1 goes there. That's how we ended up with FeCl3. Aqueous, AQ, sodium hydroxide. Sodium's in group 1, so it's a +1. Hydroxide is that one polyatomic ion that you're very likely to see that has the IDE ending. It is OH. It's on your table of polyatomic ions. It's a -1. We have a pair of 1's here, so it's just NaOH. Iron 3 hydroxide. Again, the iron 3 means it's a +3. The hydroxide, again, the OH minus. 3 goes there. 1 goes there. Remember to put the hydroxide in parentheses before you write down the 3. It does say it's a solid, so I put the S after it. And then finally, aqueous, AQ. Sodium chloride. Na is a +1, Cl is a -1. So we're going to have a pair of 1's. And it's just NaCl. As usual, if it's not something that you can figure out the formula for, I tell you what the formula is. It is a gas, so you make sure you put the G on it. Oxygen is just an element, but it is one of our diatomic elements, so you do have to put that 2 on it. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Those are the diatomic elements. It's going to produce carbon dioxide, covalent substance, carbon, 2 oxygens. And water, water is always H2O. Vapor is another word for gas. We learned how to balance equations next. Again, I'm not going to go through all the points. Do make sure all your coefficients are whole numbers. You can use fractions or decimals as part of the balancing process, but you have to eliminate them in the end by typically multiplying by 2 to all the coefficients to get rid of those halves and 0.5s. It is a good idea if you're new to balancing, if you don't understand the balancing well enough, to make sure that you list everything out that you have in your equation. So I have sodium, oxygen, hydrogen, and sulfur on my reactant side. I'm going to make sure I put the same list on the product side. And I am going to break down the polyatomic ion sulfate into its components, sulfur and oxygen. And the reason I'm doing that is because of what happens with the hydroxide. It just disappears. And the hydroxide also has oxygen in it. So that does make it a little tricky to keep track of everything. So in all cases, you're perfectly safe to break everything down individually just so you can see what's going on a little better. Now before we start, there's 1 sodium there. For the oxygens, we're going to add them together. I have 1 there, I have 4 there for a total of 5. For my hydrogens, again, I'm going to add everything together. I have 1 there, I have 2 there for a total of 3. And then for sulfur, I have 1. On my product side, again, I'm looking at it before I balance it. I have 2 sodiums. I have 1 sulfur again. For the oxygens, I have 4 here and 1 there for a total of 5. And for my hydrogens, I started off with 2. So the first thing I would do is look at that sodium being out of balance. I have 1 on the reactant side, I have 2 on the product side, so I stick that 2 there to fix the sodium. But it doesn't just affect the sodium, it does affect the oxygen and the hydrogen as well. So now I have 2 times 1, I have 2 oxygens here, plus the 4 there for a total of 6. And then it affects the hydrogens too. I have 2 here now, plus the 2 there for a total of 4. Now look at those oxygens, and you'd probably look at those oxygens and go, whoa, 6 on that side, 5 on that side. What am I going to do there? Easiest thing to do is just to go ahead and skip on down to the hydrogen. I have 4 on this side, 2 on this side. If I put a 2 there, that'll fix those hydrogens. At the same time, it is also going to fix our oxygens, because now I have 2 here, plus the 4 there, for a total of, oops, changed the wrong one, for a total of 6. So again, this is a very challenging balancing problem because of the way the polyatomic ions play out. If you can balance that one, you're doing pretty well. Again, down here, I have beryllium, I have chlorine, I have silver. This time I'm going to keep the nitrate as a single substance. And the reason I'm going to do that is because I've got the nitrate on both sides. Nothing else in that equation has nitrogen or oxygen in it. So I don't have to worry about adding those elements together anywhere. So beryllium, chlorine, silver, and again nitrate. 1 beryllium over here, and again this is before balancing. 2 chlorines over here. 1 silver, and there's no parentheses around the nitrate, so there's only 1 of those. Again, before balancing, there's only 1 Be. Again, that 2's not there yet, so there's only 1 chlorine. There's only 1 silver. And my nitrate does have parentheses on it, so I go with the number on the outside. There are 2. Doesn't matter where I start. I can start by fixing the chlorines by sticking that 2 there. That will also change the silvers. So I'll have 2 of those, as well as the 2 chlorines I need. And then I can fix both the silver and the nitrate by sticking the 2 there and doubling these up so that my equation is balanced. That's a little easier one. And again, what makes these 2 different is that in this one, my polyatomic ion is on both sides. There's only 1 polyatomic ion in that equation. The elements that are in that polyatomic ion aren't found anywhere else. What makes this one more complicated is even though we have the sulfate on both sides, we have SO4 on both sides, we only have 1 OH over here, but we don't see any OHs at all on this side. Now, one of the ways that you can fix that is by considering water to be a polyatomic ionic compound. So when you see the water over there, changing it to HOH. So instead of H2O, it's HOH. And if you do that, you'll actually see your hydroxide on both sides, like you'd expect to see. And you could, in that case, balance it out thinking in terms of hydroxide. Let me show you real quick how that would look. I would have sodium, and there was 1 of them before we balanced. I would have hydroxide, no parentheses, so there's only 1 of those before we balance. The hydrogen would be 2, and the sulfate again, because there's no parentheses, would only be 1. Over here on the product side, again, before we balance, the sodiums are 2. The hydroxide has no parentheses around it, so it's just 1. The hydrogen is right there. There's 1. And the SO4, again, no parentheses around it, so there's just 1 of those. Again, starting with the sodium, I would put a 2 there. Changes the sodiums to 2, but it also changes the hydroxides to 2. Now, if I want to fix my hydroxides, since there's 2 on this side, I can put 2 there to get me 2 hydroxides on that side. That would also fix the hydrogen. So same problem, same answer. I think a quicker solution, because I can keep track of my polyatomic ions a little clearer. But again, what you have to understand in order to do it this way is that H2O can be written as HOH, because that's what it is. It is a hydrogen ion and a hydroxide ion that have bonded together. Last one's one of those tricky ones where you can use the fractions and decimals to balance the thing out. And again, if you can balance this one, you're doing pretty well on your balancing. I'm going to go ahead and erase these coefficients. Oops. So we can work this out from scratch, so I can, again, show you how those fraction decimal things work. So I have carbon, hydrogen, and oxygen on both sides. 2 carbons, 6 hydrogens, and 2 oxygens. On the product side, there's nothing on the carbon, so that's 1. 2 hydrogens, and then again, I got to add these 2 together. I have 1 there, I have 2 there for a total of 3. So what you're likely to do here is stick a 2 in front of this to get your 2 carbons. Now your oxygens are going to be 2 times 2, there's 4 there, plus that 1 there for a total of 5. Then you move on to the hydrogen. You have 6 on this side, you have 2 on that side, you're going to stick a 3 there to fix your hydrogens. It's going to give you 6 of those. Now for the oxygens, here's where it all goes off the rails. There's 3 here, 3 times 1, and there are 4 there. So 3 plus 4 is 7, and we have that 2 there. So there's no whole number we can put in front of the oxygen and get 7. What times 2 gives you 7? 3.5. So if we put that there, we will have our 7 oxygens, and it would be balanced. But the thing is, you can't leave the 3.5 there. What you're going to have to do is go through and multiply all of your coefficients by 2 to get rid of that. So that becomes 2, 1 times 2. This becomes 7. This becomes 6. And that becomes 4. So 2, 7, 6, 4. Those are the coefficients that ends up balancing that equation. So again, a challenging one, a tricky one. If you can do those, you can pretty much do anything. All right, reaction types. Again, not going to go through all the details, the bullet points there, but when we look at this one, that's a compound. It has 3 capital letters. That's an element because it has only 1. That's a compound because it has 2 or more and has 3 capital letters. That's an element. 1 element, 1 compound on each side is single replacement. Because these are metals, it's cationic single replacement. This has 2 or more capital letters in it, so it's a compound. That's got 2 or more capital letters in it, so it's a compound. That's got 2 or more capital letters in it, so it's a compound. That's got 2 capital letters in it, that's a compound. Everything's a compound in a double replacement reaction. That is a hydrocarbon plus oxygen producing carbon dioxide and water. That is combustion. This one has no plus sign on the reactant side. That is how you identify decomposition. All right, on to predicting, one of the more challenging things that's in the unit. And again, there's some instructions there. This is basically the table that I put up on the board when I was teaching this. explaining how you figure out what to do. It all starts by looking over here on the reactant side of the equation to see what you have. I have an element here, one capital letter. I have a compound there, two capital letters. An element and a compound will be single replacement. And in single replacement reactions, like replaces like. So because our element is a metal, it will replace the metal that's in the compound, the calcium. So the calcium's getting kicked out, so it's by itself. And the lithium and the chlorine will be together in a compound. Lithium is a +1, chlorine is a -1. So we're going to get a pair of 1s here, which is why the formula ends up being LiCl2. For your elements, you just write down their symbols. Do watch out for those diatomic elements. You have to put a 2 on those. For your compounds, make sure you crisscross. Here you have two compounds. Two capital letters, three capital letters. Those are both compounds. When you have two compounds, that is a double replacement reaction. And what you have to do is just swap the positive ions around. So the sodium and the magnesium are going to swap places. Magnesium is going to be with the nitrate now. Magnesium is a +2. It's in group 2. Nitrate is on our table of polyatomic ions. It's a -1. 2 goes there. 1 goes there. Make sure you put that polyatomic ion in parentheses before you write the 2. The sodium's coming over here now to be with the chlorine. Na is a +1 because it's in group 1. Chlorine is a -1 because it's in group 17. We have a pair of 1s, so it ends up being NaCl. That is a hydrocarbon. That is oxygen. Hydrocarbons and oxygen are combustion reactions, and whenever you have a combustion reaction, your products are always carbon dioxide and water. Key here is on your elements to watch for those diatomic elements. Make sure you put those 2 on those diatomic elements, and to make sure you crisscross when you're finding out a formula, when you're figuring out a formula on your own. Obviously, we're not crisscrossing for carbon dioxide and water, but everything else is likely to be ionic, and for those ionic compounds, you've got to crisscross. In the next set, it's about the activity series. This is the activity series. We have metals on one side, we have nonmetals on the other. Reactivity decreases as you go down, so the most reactive elements are at the top, the least reactive elements are on the bottom. And the rule is when you're using an activity series to try to figure out if a single replacement reaction is going to happen, the more reactive one has to be the one that's on the outside. It's got to be the one that's by itself. So lithium, that's a metal. So we're going to compare the lithium to the other metal in our equation, the sodium. So there's lithium, and there's sodium. Lithium is higher than sodium on the list. So lithium is the more reactive one, sodium is the less reactive one. And again, if the more reactive one is by itself, if the more reactive one is the element, then the reaction is going to happen. So this will occur. The lithium and the sodium will trade places. The sodium is kicked out, and the lithium and the chlorine will combine to make a compound. I got a +1 and a -1, so it is a pair of 1s, and it is just LiCl. And my next one, I have aluminum and potassium. There's aluminum. There's potassium. Potassium is higher up the list, so the potassium is the more reactive one. So that is my less reactive. That is my more reactive. And again, the rule is if the more reactive one is by itself, if the more reactive one is the element, then the reaction happens. If the more reactive one is in the compound already, that's where it's going to stay, and no reaction will occur. This is a non-metal one because chlorine is a non-metal. We're going to compare it with the iodine. There's chlorine. There's iodine. Chlorine is higher up the list, so chlorine is more reactive. So my more reactive one is by itself. My more reactive one is the element. It's on the outside, so this reaction will occur, and the chlorine and iodine will swap places. The iodine has been kicked out. There's a 2 on that because iodine is one of the 7 diatomic elements. For the calcium and the chlorine, we have to crisscross. Calcium's in group 2, so it's a +2. Chlorine is in group 17, it's a -1. So the 2 goes there, the 1 goes there, CaCl2. Now we're going to move on to the solubility table. The solubility table is this thing here. It tells us whether something's going to be a solid or an aqueous solution. And the tricky part about this is the S in this table does not mean solid. The S in this table means soluble. And if it's soluble, it will be an AQ. I in this table means insoluble. And if it's insoluble in our equations, it would be an S. So that's the unfortunate thing about it. S in this table does not mean solid. S in this table means it's an AQ. So sodium and chlorine. Now, before we even get into this, I told you there's 4 things that are always AQs. Sodium, nitrate, potassium, and ammonium. If you see any of those 4 ions, it's automatically AQ. That's got sodium in it, so it's automatically AQ. That's got sodium in it, so it's automatically AQ. That is on the solubility table. Because if we look at sodium here and go across its row, it's all S's. And all S's mean soluble. Solubles are AQs. So really we only have to look at these 2 things. The lead and the nitrate, the lead and the chlorine. Now this is lead 2. It is the only lead that's on your table here. So lead and chlorine, which would be chloride, has an I in the box. So that's a solid. And then the other one is we already did it. So the lead and the chlorine. The lead and the nitrate we already know is an AQ. So there you go. There's a nitrate there too. So that's our solid. And again, it's because the lead and the chloride, the lead, which is right there, and the chloride that's right there has an I in the box. So in this one, there's potassium, so that's automatically AQ. There's potassium, so that's automatically AQ. You can pretty much guarantee that this is AQ because these 2 things wouldn't react very well if this were a solid. But we can confirm that. Calcium and chloride. There's calcium. There's chloride. There's an S in the box. So that is an AQ. Over here is calcium and phosphate. So again, we're going to look it up. Calcium's there, phosphate's there. There's an I in the box. Insoluble. So that's our solid. NH4 is automatically an AQ. Again, NH4 is automatically a KQ, so it's just these 2 things that we're worried about. The barium chloride and the barium sulfate. There's barium. Barium chloride is an AQ. Barium sulfate is an S, a solid. And again, generally speaking, you can count on both of these being AQs because if they weren't, they probably wouldn't react with each other. Typically, there's only one solid on this side. So if you're in a situation like this where you've already determined that that's got potassium in it, so that has to be an AQ, well, this must be your solid. And that's the way it works 99% of the time. Net ionic equations. When we do a net ionic equation, we start off with a complete ionic equation first. So what we're going to do is we're going to take all of our AQs and just our AQs and break them down into positive and negative ions. So MgOH2 is an AQ. That is a positive magnesium ion. Specifically, it's a +2 because it's in group 2. OH is our negative ion. It's on our table of polyatomic ions. It's a -1. And again, we're going to treat hydrogen like it's a metal. It's in group 1, so it's a +1. Chlorine's in group 17, so it's a -1. We're going to break this down. Magnesium is +2 again. Chlorine is a -1 again. The water we're not going to break down because it's a liquid. Again, we only break down AQs. That whole thing right here is a complete ionic equation. Now we look for what are called spectator ions. Spectator ions appear on both sides of the equation. We cancel those out. We have an Mg plus 2 there. We have an Mg plus 2 there, so those are going to cancel out. We have a Cl minus and a Cl minus. Those cancel out. What we're left with is our net ionic equation. Do make sure it's balanced. And this one is. 1 oxygen on each side, 2 hydrogens on each side. Moving on to the next one. Again, we break down all the AQ, so the NaCl gets broken down to an Na plus 1 and a Cl minus 1. The lead nitrate gets broken down. Now, you do have to figure out what the charge is on the lead. It's another Roman numeral thing again. Nitrates on our table of polyatomic ions, it's a minus 1. We always use the number on the outside. So there's 2 of them, so its total charge is negative 2. Remember, if there's no parentheses there, there's just 1. That means this side has to be positive 2. There is only 1 lead. So it is lead 2 nitrate. So the lead's a plus 2, the nitrate's on our table of polyatomic ions, it's a minus 1. We don't break down the PbCl2 because it's a solid. We break down the NaNO3. You can cancel out the spectator ions, sodium's on both sides, nitrates on both sides. What's left is your net ionic equation. We do need to balance it. Because there are 2 chlorines over here, we had to put a 2 in front of the Cl to make it balance. You can also think of that in terms of charge balance. The charges have to be the same on both sides. And because there are no charges over here, these charges have to cancel out as well. Because that's a plus 2, we need a minus 2 for those charges to cancel. Just another way you can think about it. So we have to stick that 2 out in front of the chlorine to get the negative 2. It's a little higher level thinking way of doing it. Again, I'm not going to go through all the bullet points because there were a lot of notes there for the energy changes in chemical reactions. That is a potential energy diagram. This is an uphill reaction. Our reactants have less energy than our products. That is what an endothermic reaction is. Which line represents the activation energy? Activation energy is from the reactants to the highest point. So from the reactants down here, which are B, to the highest point, the activated complex, that's A. That line C there is the activation energy. So B, those are the reactants. D, those are the products. A is what we call the activated complex. It's the highest point. And again, your activation energy is from your reactants to your activated complex. This is your enthalpy change, your delta H. Delta H is the difference between the products and the reactants, between D and B. In an endothermic reaction, your delta H, your energy, goes on the reactant side because it goes into the reaction. Delta H, again, is the products minus the reactants, so 175 minus 150. It is a positive 25. Delta H is supposed to be positive in an endothermic reaction. And what a catalyst does is lower the hill. The catalyst would make the hill a little easier to get over, so something like that. It lowers our activation energy, so now our activation energy is just from here to here. Makes the reaction easier to take place, makes the reaction occur faster. And again, that's a lot of notes. Make sure you study those notes, but most importantly, make sure you can interpret those potential energy diagrams.